All right, let's look at section 7, I think, of chapter 14. So in this chapter 14, we only discuss one application of multivariable calculus, the differentiation part, how to find maximum and minimum values of a function. Of course, we have many applications of differentiation of multivariable calculus. But on the other hand, we still need to get to the integration part. So we only spend maybe about a week on application problems. And also, the content of application to the optimization problems is essentially parallel to what we had in Calculus 1. So we will also try to recall what we had in the past. Okay, so in single variable case, how can we find maximum or minimum? So at that time, we also looked at local extrema, local max, and local min. And we call these points over here critical values. We find candidates first from the so-called first order conditions, and then we use second order condition to test. So we have the derivative is either equal to 0 or the derivative does not exist. Okay, and these are called first order conditions, especially the first one, because first order derivative, this is called first order condition. And then we have critical values. From here we have critical points or critical values. And in dimension 1, to tell whether a point is local maximum or local minimum, we also had a derivative test. We say if derivative is increasing, then it's local minimum. If the derivative is decreasing, then it's local maximum. And we don't have this kind of tests for multivariable functions. And we will only use second order conditions. Okay, so for second order condition, what we have is that if your second order derivative is positive, then we have local minimum. Okay, if your second order derivative is negative, then we have local maximum. And it's pretty easy to remember this rule because we can just remember polynomials of degree 2. If you have a quadratic function like the x squared, and then we have local minimum, right? And if we have negative x squared, then we have a local maximum. And you look at the second order derivatives, and then we know the tests. And if second order derivative is 0, then this test fails. We have to use other kind of methods. So this is 1D. Now, we have 2D, 3D, and in general, ND. We will just use 2D to illustrate in this textbook. And later on, if we have time, we're going to visit the n variable case. But we will only just make an extension, not really practice over examples. So now, if you want to find critical values, so these are called candidates for the local max and local min, and you look at first order derivative, now you have 2 equal to 0, or one of the first order derivatives does not exist. Okay, and there is a reason for that. You can just use a local max to look at it over here. If you have a local max, then 2 derivatives, partial derivative must be 0. Both tangent lines in the x or y direction should be horizontal. So this is how we determine if it's a critical value. But from critical values, we need to determine whether it's local max or local min. And here we have so-called the second order conditions. And let's look at the second order conditions. Second order conditions are dependent on so-called the second order approximation of a differentiable function. Earlier, we looked at the function's linear approximation over here. This part is the linear approximation that we discussed. And this part over here is the second order. Okay. So at a critical value, you can see fx and fy, these two derivatives are 0. So we have f of xy is approximately f of 0, 0, at 0, let's say, and plus 1/2. And then here we have the second order terms over here. We can see that's fxx times x squared. All these double derivatives are evaluated at 0. And then plus fyy and y is 0. So it depends on this huge second order term whether it's positive or negative. If it's positive, then we have local minimum. If it's negative, then we have local maximum. Okay, so that's how we got these second order conditions. And the theory isn't really too complicated, but we will just try to first remember these second order conditions and then practice over a few examples. After we practice a few examples, then we're going to come back to reason why, or just use a little bit kind of intuitive approach to discuss why these conditions are conditions for local maximum or local minimum. Okay, so for local minimum, we have two conditions. First, we form this difference. If you think about this, is exactly determinant. This d over here is the determinant fxx, fyy, and fxy, fyx. Now we know fxy, yx the same, so this is fxx, fyy minus fxy squared. Okay. So if the determinant is bigger than 0, then we look at also on the diagonal. fxx or f partial derivative yy, if both of them are positive, then it has to be local minimum. Okay. And in this kind of case, this matrix actually is called positive definite. xx, fxy, fyx. This matrix is called a positive definite. Okay. So if it's positive definite, that's like second order derivatives positive, and then we have local minimum. Now, if f double derivative with respect to x is negative, but this determinant is still positive, so one negative, one positive, then this matrix is actually negative definite, and then we have local maximum over there. So this matrix over here, this hashing sometimes we say is negative definite, and then we have local maximum. If this determinant is less than 0, then it has to be a saddle, not a local minimum or not local maximum or local minimum. So a saddle, that means you have directions, the value is going to decrease, and you have also directions, the values are going to increase. Okay. I think we're going to stop over here for a break just from the theory, and then we're going to do the examples.